Hello everyone, welcome to lecture 22 and this is the continuation of the first part. So, we were talking about the snow grain sizes and then we have also seen how the hyperspectral remote sensing is being used by various researchers in identifying the snow grain sizes. So, we will try to see some more detail about this. So, this is our work which is from South Lonak Lake, and because of the Gloff event this particular area was studied. So, the South Lonak Lake is a moraine dammed glacial lake located in the North District of Sikkim, India. The lake is east to west elongated and situated at the tongue of South Lonak Glacier at an elevation of 5200 mean sea level in the Lonak Valley. So, the water which is coming to the South Lonak glacial lakes, they are from these glaciers. After the lake burst on 4th October 2023, the length of the lake was reduced by 48.4% that we have identified using the satellite data analysis. So, we have used the Prisma data and this is a single satellite sensor that has been used, which has the repetition cycle of roughly 29 days. It is a sun synchronous low earth orbiting satellite. Push broom sensors are used here with 240 contiguous spectral bands, which is measured in 400 to 2500 nanometer wavelength range. So, the 66 spectral bands are in the visible and VNIR wavelength range, whereas 173 bands are in the SWIR short wave infrared range. The Prisma has a coherent spectral resolution of about 12 nanometer, a narrow bandwidth and 30 meter spatial resolution on a 30 kilometer swath width, right. So, we have used the Prisma L2D product which is acquired on 8th October 2023 and this was downloaded from this particular website. So, you can just simply register it and then after that you can download the data sets. So, here you can see the basic details about this data. So, the Prisma hyperspectral sensors that is been used here, this is the spectral resolution and the date of acquisition. So, in this study we tried to identify different wavelength ranges. So, we have a reference grain sizes. So, we have used the different grain sizes. So, the first one is the frost, fine grain, medium grain and the coarse grain. So, we tried to use this Prisma data, how we can utilize this data set to classify our study area into different grain sizes, right. So, the used data was basically the L2D data which was orthorectified and which is L1 product, which is nothing but the bottom of atmosphere reflectance. So, we have used the snow density here which is 250 kilogram per meter cube, and this is the methodology that have been used in our study. So, here you can see this method requires a hypercube. So, here the Prisma hyperspectral data, we also call it hypercube, that has been used, and then the GHU spectral library was referred to have the spectral signature of different grain sizes. Before snow grain size mapping, the GHU snow end members are resampled to Prisma satellite spectral resolution, that is basically 12 nanometer, but the GHU library has the 0.01 nanometer sampling. So, we have to convert it to 12 nanometers so that it will match with the Prisma satellite data. After mapping snow grain size, the corresponding energy absorbed by each grain size is estimated using the absorption band area method. So, the equation is shown here. The absorption band area utilizes the fact that both liquid water and ice have absorption feature around 1 micrometer in the spectral region, right. The noise induced fluctuations are averaged then. by integrating the absorption feature, yielding a precise estimate near the actual value, right. So, where AB is the absorption band area and the RB is the reflectance spectrum and RC is the continuum removed spectrum. So, that has been used in this equation. The equation within the integration is called the scaled band depth. The energy absorbed by mapped snow grain size and GHU snow end member is compared to see the trend among the mentioned snow grain sizes. In the absence of in situ snow spectra, this absorption band area method is chosen as a validation technique, taking GHU snow grain size spectra as our reference data, right. So, when we cannot visit the site and then we do not have any information from the surface, then in that condition this is a very good method to validate. The NDSI threshold for snow cover is 0.4, generally taken in the literature, right, for the snow cover. The default value of 0.05 is taken as the threshold of SID based snow grain size classification. The SID based classification shows that the majority of the grains in the study area had coarse and medium grain sizes with much less frost and fine grain size present in comparison. So, here you can see the 31% is medium grain size and 61% is the coarse grain, whereas the fine and frost is 2 to 6%. So, here you can see the spatial distribution of different grain sizes present in the study area that have been identified. So, the GHU spectral library at satellite resolution, which is shown here, right, and then we have different spectra. The B to E is the continuum removed spectra of fine granular, frost, medium granular and coarse granular snow, whose y axis is the continuum removed spectra. So, you can see the continuum removed is here, the 1 is the maximum value and all the spectras are coming from the 1. Then the scale absorption depth of the snow grain size, which is given in the F, whose y axis is the scaled band value and x axis is the wavelength. The vertical line parallels to y axis is at wavelength equal to 1.03. So, from this study we found that the coarse grained size snow has the lowest reflectance while frost has the maximum reflectance. When the grain radius rises, the reflectance spectrum and the continuum removed reflectance both drops, while the scaled area of the absorption feature grows with the grain size, which is correlated with the absorption efficiency. In other words, a change in the grain size helps to identify the surface feature of snow such as melt and snowpack energy balance. When the absorption depth of each grain size were investigated using continuum removed, it was observed that part of the 1.03 micrometer spectral region, there are two more prominent absorption depth, that is near to 1.5 and 2 micrometer. However, these two new wavelengths are susceptible to water vapor and carbon dioxide absorption. So, they are excluded from the grain size mapping. So, here further we have some box plots which shows the absorption band area for each snow grain size. The marked value shows the GHU snow spectral energy absorbed by each snow granular and frost. And here the underlying snow should have been exposed to the surface following the glow-off occurrence, and this grain size should generally be considered as coarse grain, as this analysis surface layer demonstrates, right. So, this I wanted to show you the example how hyperspectral remote sensing can be used in snow grain size mapping. To summarize this work, the snow grain size mapping for the South Lonak Glacial Lake region has been studied using Prisma data. The spatial subset of the hyperspectral data has been confined to the study area. The whole image was not used. The SID method utilizing Prisma and JHU snow spectral library for fine frost, medium and coarse granular snow has been employed for snow grain size mapping. To characterize the snow surface characteristic including melt area and snowpack energy balance, the absorption band area method is applied to map the snow grain size. The wavelength range centered at 1.03 is suitable for understanding the grain size. So, remember this is the main conclusion. The energy absorbed by the mapped snow grain size is consistent with JHU snow grain size spectra and Himalayan field circumstances of melting in the ablation period of October. Now, we will try to understand how remote sensing can be used in snow contamination study. So, the snow contamination refers to the presence of various pollutants and foreign materials mixed with snow. So, here you have different examples. This is from our field, and to just understand the basics, you see this is a fresh snow, right? It is not contaminated here, the left hand side. So, whatever energy is falling here, the maximum energy will get reflected. But when it comes to this contaminated one, what will happen? The less amount of energy will be reflected back. So, if you talk about the total energy budget, here ideally this should reflect so that our atmosphere will not have, or our earth system will not have any additional energy, right? But because of this contamination, they were supposed to reflect, but they are not reflecting. So, they are appearing in dark and the albedo has been reduced. So, if the albedo is reduced, more absorption will be there, and that will lead to the melting of this glaciers or the snow. Snow is considered contaminated when foreign materials are deposited or mixed with it, accelerating melting and significantly impacting the snow cover radiative balance, such as enhanced melting rate result in a reduction in freshwater sources at the catchment level. In optical remote sensing, snow contamination is widely studied using normalized difference index called the snow contamination index. This is based on the finding that the impact of snow contamination diminishes with wavelength and is most noticeable in the visible spectrum, which is 0.3 to 0.7, or sometimes it is 0.4 to 0.7 micrometer. However, the study of snow contamination using optical remote sensing is hindered in the Himalayan terrain due to enduring cloud cover in the region. That is why we have explored the potential of SAR data in such studies, and here we have used the Sentinel-1 data set because it has capability to measure in all weather condition. So, this particular study focuses on the SAR backscattering behavior at the C band of clear and contaminated snow for March 2022 in a part of the eastern Himalayas of Arunachal Pradesh, India. An attempt has been made to utilize Landsat 7. So, we have used optical data also here and the Sentinel-1 to study the snow contamination. Snow contamination can accelerate melting and majorly impact the radiative balance of the snow cover, that we have understood how it is behaving when there is a change in the albedo. According to them, understanding the connection between the cryosphere, the atmosphere and the climate depends on how a snow impurity affects snow albedo reduction. Further, the deposition of black carbon accelerates the melting of the snow, because nowadays we have more pollution, and if there is a wind circulation which brings the black carbon from the mainland to these higher altitude, that will get mixed with the snow, and then we will have the more impurities and the contamination, resulting in decrease in freshwater sources at the catchment level. Also, it will increase the melting. So, for this we have selected the Arunachal Pradesh, and here you can see these stars where we have conducted our field investigation to identify different types of snow which is shown in these figures, right. So, for this we have used synthetic aperture radar data. So, we have Sentinel-1 which is dual polarimetric, VV and VH that is been used. SLC interferometric wide IDW swath mode data is used, and this is basically the C band data, and the spatial resolution is 5 by 20 meter, and the date of acquisition is 3rd September 2021, and the next one is the 14th March 2022. As I mentioned earlier, we have also used the optical data. So, we have the multispectral data from Landsat 9 level 1 data, and the 11 bands were used here, and the spatial resolution of this is 30 meter, and the date of acquisition is 14th March 2022, which is matching with our Sentinel-1 data, right. So, for that we have used NDSI, NDFSI and S3 band indices, and then finally we have used the SCI, right. So, the threshold for each snow index is based on Saptarishi et al. 2022. SAR backscattering values are obtained using polarimetric technique. So, here the polarimetric SAR has been used. So, as I mentioned in the previous slide, Sentinel-1 is the polarimetric data, right. So, that has been used, and based on that the contaminated and clear snow was mapped, and here the polarimetry has been utilized. So, you can see the VH and VV that has been used to identify. For the snow contamination, the snow and non-snow area that has been seen. So, how the backscattering values are changing. So, these statistical analysis have been performed to finally arrive at a decision that how the backscattering coefficient can be used in identifying the contaminated and non-contaminated snow. So, the snow condition in terms of snow contamination is studied using multispectral L9 and SAR S1 data set for the Mechuka region in Arunachal Pradesh, India. The range of SAR backscattering for snow and non-snow region is obtained using the resultant snow cover map. The snow cover region have comparatively lower backscattering than non-snow areas. So, this you can see in any of the microwave data set. The contaminated snow has a comparatively higher backscattering value than clear snow. So, now here we have come to a conclusion that the contaminated snow has comparatively higher backscattering value. The average wetness for both snow classes ranges from 3 to 5% of volume, in contrast to the visible electromagnetic wavelength region, where contaminated snow exhibit a lower reflectance value than the clear snow. The SAR backscattering for contaminated and clear snow exhibit opposite features in the microwave region of the C band. It is observed from the analysis that the key parameters influencing SAR backscattering over contaminated snowpacks are local incident angle, snow wetness and the surface roughness. So, these three are used. Now, we will talk about the snow depth. So, the snow depth refers to the vertical distance from the surface to the ground of it, right. So, assuming this is the lowest surface where we have the rocks and soils, right. So, then in that case this will become the depth of the snow. Snow depth is a critical parameter for understanding the extent and volume of snowpack, which plays a key role in hydrological studies. It is an essential indicator for assessing snow water equivalent. It provides valuable insight for water resource management because the thickness is more, if the depth is more, that indicates it has more potential to supply the water over time. Snow melt forecasting and various hydrological application requires this snow depth information. Under these circumstances, monitoring snow condition has proven to be especially useful using satellite remote sensing techniques. The snow parameters have previously been retrieved by researcher employing a variety of optical and radar remote sensing data set. Particularly, optical remote sensing encounters constraint in foggy condition prevalent in snow covered regions for much of the year. In contrast, radar remote sensing functioning within the microwave spectrum, which is P, L, C and X bands, offers an advantage by acquiring images even under cloud cover. So, the factors which are affecting the snow depth, they are the snowfall, temperature, wind, then we have solar radiation, then next is rainfall, the liquid, right, and then snow density, and finally it is topography. So, together they work on this system and then they define or they control this snow depth. So, how do we measure it in the field? So, one example is the manual measurement, that is the simplest one. You go to the field, put a snow stake and then you measure how much it has occurred in the last 1 year or in last season, right. So, for that you need to have a reference point. In another one we have the automated measurement. So, here we are using different sensors that send the pulses and then they measure the height of this particular area, right. So, we have known value for the last year, from there how much accumulation has occurred, that can be identified. So, here you can see we call it snow stake, but with the advancement in the technology we are also using the ultrasonic or the laser sensors mounted over the snowpack. These sensors emit pulses and measure the time it takes for the echo to return from the snow surface, thus determining the distance to the snow. By knowing the sensor height, the snow depth can be calculated. So, as I mentioned, it will send the pulses, then it will reach to it and then they will derive the change in the storage, right. So, for this snow depth study, we have done a field work where we have trekked for 96 kilometer and we reached to this Rathong glacier, where we have tried to install the snow stake, and that is a manual snow stake. So, you can see this is during the ablation period. So, this surface is not having the snow, but this is the part of the main glacier body. So, this is the Rathong glacier, right. So, here we have tried and we have installed, and every year we have to collect the information how much precipitation has occurred with respect to last year or last season. So, this is how we are trying to do for the snow depth. But apart from that, we have also used the remote sensing techniques to estimate the snow depth information, and that we validate using our field information. So, with this I will end this lecture and we will continue the application of remote sensing, particularly in depth studies, in the next part. Thank you very much.